To understand the longest-lived stars in the universe, we must first leave behind almost everything human instinct associates with grandeur. We look upward and imagine power as brightness, size, violence, blue-white flame, a star so brilliant that distance itself seems unable to weaken it. Yet the stars most likely to inherit the far future are quiet, dim, and often invisible to the naked eye. They do not dominate the constellations. They rarely become the subjects of myth. They sit in the background of the galaxy, small red embers scattered through the dark, burning with a patience almost beyond language. These stars are called red dwarfs. They are the smallest true stars, bodies massive enough to ignite hydrogen fusion in their cores, yet modest enough to spend their fuel with extraordinary care. A star like the sun burns with a confidence that feels eternal to us, but even the sun is brief on cosmic scales. It will exhaust the stable part of its life in roughly 10 billion years, swell into a red giant, and leave behind a white dwarf, a cooling remnant slowly fading through the ages. Red dwarfs follow another rhythm entirely. Their light is weaker, their temperatures lower, their surfaces cooler, their mass far smaller. Their weakness is also their endurance. In the cosmic story we usually tell, the great events belong to giants. Massive stars ignite, rage, forge heavy elements, and die in spectacular supernovae. They carve nebulae into glowing scars. They seed space with oxygen, carbon, silicon, iron, the architecture of worlds and bodies. Red dwarfs rarely offer such theater. They are too light to explode as supernovae. They do not spend their lives racing toward catastrophe. They remain generation after generation, long after the stars we notice first have vanished from the visible universe. A red dwarf is a lesson in scale, but a strange one. It is small enough to be overlooked and durable enough to outlast almost every luminous thing. It reminds us that the future of the universe may belong less to the spectacular than to the persistent. When the grand blue stars have died, when sun-like stars have swollen and collapsed into quiet embers, when the spiral arms of galaxies have grown older and dimmer, the red dwarfs will still be burning. Their faint red light may become the last common form of starlight in existence. This is the story of those stars. The small fires that may outlive everything familiar, the slow engines that turn hydrogen into time, and the strange worlds that may orbit them through epochs longer than the entire present age of the cosmos. It is also the story of what happens when endurance becomes its own kind of power, when the universe stops being a place of beginnings and becomes a place of leftovers, and when the last stars are no longer the brightest ones, but the ones that refused to hurry. Red dwarfs are not rare curiosities. They are believed to be the most common stars in the Milky Way. The galaxy is filled with them, yet most remain unseen from Earth without instruments because their light is faint and red, easily swallowed by distance. Our night sky gives a distorted impression of the stellar population. The stars visible to the naked eye are often the luminous exceptions, the nearby or intrinsically bright bodies whose light can cross interstellar space and still leave an impression on human vision. The most numerous stars are the ones our eyes mostly miss. This is one of the quiet tricks of astronomy. The visible sky feels democratic, as though it reveals the universe according to abundance. In reality, the eye is biased toward brilliance. A rare giant star may be seen across immense distances while countless smaller stars vanish into darkness. Red dwarfs make up much of the stellar background of the galaxy, but they rarely announce themselves. They are the hidden majority, the low-burning population beneath the grand architecture of the Milky Way. Their names often sound less poetic than the names of bright stars, because many were discovered through surveys rather than myth. Proxima Centauri, Barnard's Star, Wolf 359, Lalande 21185, TRAPPIST-1, Teegarden Star. These are nearby suns, but most people will never see them directly. Some are among the closest stellar neighbors to Earth, yet they appear absent from the sky. The closest star to the solar system, Proxima Centauri, is a red dwarf too faint for ordinary sight. Our nearest stellar companion hides beside the brilliance of Alpha Centauri, visible only through careful observation. Their invisibility has shaped our imagination. Humanity built its early cosmology from what could be seen, and what could be seen was rarely representative. We named the bright stars, tracked their seasonal movements, navigated by them, folded them into gods, hunters, animals, queens, and warnings. Red dwarfs remained mostly outside that ancient language. They were present, abundant, and close, but too dim to be woven into the first maps of meaning. Modern astronomy changed that. Telescopes, detectors, infrared surveys, and patient measurement revealed a galaxy far more populated by small stars than the human eye had suggested. The universe had hidden much of its common life in faintness. Red dwarfs became central to questions that once belonged to brighter suns. How long can a star live? How many planets may exist? Where might life endure? And what kind of light will remain when the age of familiar stars has passed? A star survives by balancing two immense forces. Gravity pulls inward, trying to crush the star under its own weight. Fusion pushes outward, releasing energy as hydrogen nuclei merge into helium. In a star like the Sun, this balance can remain stable for billions of years. Hydrogen burns in the core, energy moves outward, and the star shines steadily enough for planets to orbit, climates to settle, oceans to persist, and life to build fragile complexity under a predictable light. Red dwarfs obey the same basic physics, but their smaller mass changes everything. Because they are lighter, their central pressures and temperatures are lower than those of the Sun. Fusion proceeds more slowly. Their luminosity is far weaker. A red dwarf spends its fuel at an extremely modest rate, and that modest rate becomes the foundation of its immense lifetime. It is the stellar equivalent of a candle lowered so far that it can burn across ages no human chronology can comfortably hold. There is another reason for their endurance. In many low-mass red dwarfs, convection can mix material through much of the star, and in the smallest ones through nearly the entire interior. This matters because a sun-like star can use only a fraction of its hydrogen during its main sequence life. The core burns, helium accumulates, and eventually the structure changes. A fully convective red dwarf can keep bringing fresh hydrogen into the regions where fusion occurs. It uses its fuel more completely and more efficiently. This makes the red dwarf a deeply different kind of star. The Sun is powerful, generous, and temporary. A red dwarf is faint, controlled, and almost absurdly long-lived. Some of the smallest red dwarfs are expected to burn for trillions of years. Estimates can reach into the tens or even hundreds of trillions of years for the lowest mass stars, depending on the models used and the exact mass considered. Since the universe is only about 13.8 billion years old, no red dwarf has yet reached the end of its natural main sequence life. Every red dwarf ever born, if left undisturbed, is still young by its own standards. This fact is difficult to absorb. The oldest red dwarfs in existence are ancient compared with Earth, ancient compared with the Sun, ancient compared with biological evolution, civilization, language, and memory. Yet in the timeline of their own lives, they have barely begun. The universe has not existed long enough to show us what the death of the smallest red dwarfs truly looks like. Their endings belong to the far future, to a chapter of cosmic history that no telescope can observe directly because it has not happened anywhere yet. Astronomy often studies the past. Light takes time to travel, so looking outward means looking backward. A distant galaxy appears as it was millions or billions of years ago. Ancient light reaches us after crossing an expanding universe, carrying information from epochs long before Earth formed. Yet red dwarfs create a stranger problem. Their most important future lies beyond observation because the universe has not had enough time to produce it. For massive stars, the full life cycle is visible across the cosmos. We see them forming in nebulae, burning intensely, swelling, collapsing, exploding, and leaving behind neutron stars or black holes. For stars like the Sun, we observe analogs at different stages. We see young solar-like stars, middle-aged stars, red giants, planetary nebulae, white dwarfs. The galaxy contains enough examples for astronomers to reconstruct the arc. Red dwarfs frustrate that method. The smallest ones have lifetimes so long that no example has yet evolved to completion. This means every red dwarf is, in a sense, unfinished evidence. We understand them through physics, models, stellar populations, mass, temperature, luminosity, and the behavior of matter under pressure. We can estimate their futures with strong scientific reasoning, but we cannot point to an ancient dead red dwarf and say, "Here is the final form." The cosmos has not yet grown old enough to provide the sample. This gives red dwarfs a peculiar philosophical weight. They are among the most ordinary stars in the galaxy, yet their destiny belongs to a future so remote that it makes the present universe feel newborn. When we say a red dwarf may live for trillions of years, we are speaking across a scale that dwarfs the age of galaxies as we currently know them. The entire history of Earth, from molten formation to oceans, microbes, forests, mammals, human speech, satellites, and interplanetary probes, would fit into an early flicker of a red dwarf's life. The universe is old, but it is not equally old for all things. For massive stars, 13.8 billion years is more than enough time for countless generations to live and die. For the smallest red dwarfs, it is only a beginning. They are not relics of a dying universe. They are young participants in a cosmic story whose longest act has not started. Imagine the far future. The sun is gone. The bright blue giants have vanished almost everywhere because such stars live quickly and die quickly. The great star-forming regions have faded as galaxies exhaust or lose the gas needed to build new suns. The universe continues expanding. Distances lengthen. Galaxies drift beyond one another's horizons. The sky, once crowded with formation and violence, becomes quieter. In that future, red dwarfs remain. They continue to glow in the long dimming of the cosmos, less like torches than embers preserved in ash. Their light is weak, but there may be many of them. The Milky Way, if it has merged with Andromeda and settled into a larger aging galaxy, may still contain vast numbers of these stars. Around some of them, planets may continue to orbit. Some worlds may be frozen, burned, stripped, or tidally locked into strange climates. Others may hold atmospheres, oceans, or chemical complexity under red light. The far future of starlight may be red. This is one of the most striking implications of red dwarf longevity. The universe we see now is rich in variety. Blue stars, yellow stars, orange giants, red giants, white dwarfs, nebulae, star clusters, luminous galaxies. Over deep time, many of these features fade or transform. Red dwarfs are expected to remain among the final stable furnaces of fusion. They may become the ordinary suns of the late universe, the last places where hydrogen still turns into light. There is a melancholy beauty in that image. The early universe was dominated by expansion, heat, the formation of atoms, the first stars, the first galaxies, the first heavy elements. The middle universe, the one we inhabit, is rich in stars like the sun and planets like Earth. The late universe may belong to dimmer, smaller, older systems. Time will make the cosmos less spectacular to human eyes, but perhaps more profound. The last lights may be modest, persistent red. A red dwarf does not need to dazzle the universe to matter. Its importance grows with time. In an age of stellar abundance, it is easy to ignore. In an age of cosmic scarcity, it becomes a sanctuary of fusion. A small star that once disappeared into the background may become, after unimaginable ages, one of the last sources of warmth anywhere. Because red dwarfs are faint, their habitable zones lie close to the star. A planet must orbit near enough to receive sufficient energy for liquid water, if water and atmosphere are present. This creates a very different architecture from the solar system. Earth receives warmth from a sun far enough away that our year lasts 365 days. Around many red dwarfs, a potentially temperate planet may orbit in days or weeks. Its sun would loom larger in the sky, redder and dimmer, yet physically close. Closeness changes a planet's fate. Many planets in red dwarf habitable zones are expected to become tidally locked, with one hemisphere always facing the star and the other turned permanently toward space. The day side may live under a steady red sun, while the night side lies beneath eternal darkness. Between them, a ring of twilight may circle the planet, a borderland where light arrives low and constant, where climates might depend on atmosphere, oceans, winds, and heat transport. Such worlds have become some of the most fascinating targets in modern exoplanet science. Systems like TRAPPIST-1 show that small red dwarfs can host multiple rocky planets packed into tight orbits. Proxima Centauri has at least one known planet in the broad region where temperatures invite speculation, though habitability remains uncertain. Around these small stars, astronomy has found some of the nearest rocky worlds available for study. Their proximity and frequent transits make them tempting targets for telescopes seeking atmospheres. Yet red dwarf planets face serious challenges. Young red dwarfs can be magnetically violent. They can flare, releasing bursts of radiation that may erode planetary atmospheres, damage surface chemistry, and complicate the emergence or survival of life. A planet close enough for warmth may also be close enough to suffer. Habitability around red dwarfs is therefore a question of balance: atmosphere versus erosion, magnetic protection versus stellar storms, water retention versus early loss, chemistry versus radiation. This tension gives red dwarf worlds a dramatic quality. They may be among the most common rocky planets in the galaxy, orbiting the most common stars, with lifetimes vastly longer than Earth's future around the Sun. They also may endure brutal beginnings. If life can arise or survive there, it may have more time than life around sun-like stars could ever receive. But time alone is not a guarantee. 1 trillion years means little to a planet stripped bare in its youth. Red dwarfs are often described as stable because their lives are long, but their youth can be turbulent. Many are magnetically active, especially when young. Their surfaces can be marked by star spots, their magnetic fields can twist and release energy, and their flares can send radiation across nearby space. Since planets in the temperate zone orbit close to the star, they may receive these eruptions at high intensity. The same closeness that grants warmth can also expose them to danger. This creates one of the central paradoxes of red dwarf habitability. The star offers enormous time, yet the early environment may be hostile. A young world may need an atmosphere thick enough to survive erosion, a magnetic field strong enough to deflect charged particles, volcanic outgassing sufficient to replenish lost gases, or an ocean and crust capable of absorbing damage. The details matter. Mass, composition, orbit, stellar age, flare frequency, and atmospheric chemistry all influence whether a planet becomes a living world, a sterile rock, or something in between. Science has moved beyond the simplest early assumptions. Tidal locking was once treated as a near-automatic sentence for habitability because one side would bake and the other freeze. Climate modeling has complicated that picture. With a sufficient atmosphere, heat can move from day to night. Clouds on the day side may reflect stellar energy. Oceans may redistribute warmth. A tidally locked planet could be strange without being impossible. It might have permanent weather patterns, immense winds, a stable substellar region, frozen nightside reservoirs, and habitable twilight zones. The question of life around red dwarfs remains open because the universe rarely answers in simple categories. Some red dwarf planets may be ruined early by radiation. Others may endure. Some may lose atmospheres, then rebuild them through volcanism. Some may form farther out and migrate inward. Some may orbit unusually calm stars. Some may possess oceans beneath ice, protected from direct stellar violence. Each system carries its own history. For a filmmaker, this is powerful material. A red dwarf world is not simply an Earth under red light. It is another grammar of existence, a sky where the sun never rises or sets, A planet where dawn is a place rather than a time. A civilization, if one ever existed, might build its calendars around flares, orbital resonances, atmospheric tides, or the slow migration of climate zones. Under such a star, life would learn patience from the sky, but also caution. The sun feels eternal because human life is brief. Every generation has lived beneath the same kind of daylight, and the sun's change across history is too slow to enter ordinary perception. Its constancy is the background of almost every human idea of time. We measure days by its rotation across our sky, seasons by Earth's orbit around it, and deep history by the energy it provided to climate, photosynthesis, and evolution. Yet the sun is temporary. It is already middle-aged. In several billion years, it will grow brighter, changing Earth's climate long before it reaches its red giant phase. Oceans may evaporate, surface habitability may end. Later, the sun will swell, shed its outer layers, and leave behind a white dwarf. Earth's ultimate physical fate remains a matter of modeling, but its living future is limited by the evolving star that made life possible in the first place. The sun gave Earth a stable window, and that window was enough for life to begin, adapt, diversify, collapse, recover, and eventually produce creatures capable of asking what kind of star made them. But in the context of red dwarfs, the sun's generosity is brief. A world around a quiet red dwarf, if it survived the early violence and retained the right conditions, could theoretically have far longer for chemistry and biology to unfold. Its evolutionary clock might tick beneath red light for timescales that make Earth's entire biological history seem compressed. This raises a haunting possibility. Perhaps life around sun-like stars appears first because such stars provide relatively gentle early conditions. Perhaps life around red dwarfs, if common, emerges later because their planets need time to recover from hostile youth. The universe may be too young for some of its most numerous habitats to reveal their full potential. Civilizations around red dwarfs, if they ever arise, may belong less to the present cosmic era than to epochs far ahead of us. Humanity appeared under a star that will die comparatively early. We were born in a bright middle age of the universe, under a yellow-white sun that spends its fuel at a respectable but finite rate. Red dwarfs suggest another kind of cosmic inheritance. Worlds where time is abundant beyond imagination, where the main challenge may be surviving the beginning rather than racing against the end. If planets around red dwarfs can remain habitable, they may become some of the last habitable islands in the universe. This idea is speculative, but it follows naturally from stellar lifetimes. As sun-like stars age and die, any civilizations or biospheres dependent on them face relocation, adaptation, or extinction. Around red dwarfs, stable fusion may continue long after the stars familiar to us have ended their main sequence lives. A planet in the right orbit around a calm red dwarf could receive energy for far longer than Earth ever will. The late universe may therefore contain quiet systems where life, if it exists, has had enough time to become ancient beyond comprehension. Imagine oceans under crimson daylight, continents shaped by tectonics over tens of billions of years, atmospheres altered by biology across epochs longer than the age of the Milky Way today. Imagine intelligence arising not under a bright young sky, but in a galaxy already dimming, with the memory of larger stars preserved only in science, myth, or fossil radiation. There is also a darker version. Red dwarfs may last long, but their planets may fail. Atmospheric loss, tidal locking, flare damage, water loss, geological stagnation, or orbital instability may leave many red dwarf worlds barren. In that case, the last stars would shine over dead planets, illuminating surfaces that endured without ever becoming alive. The universe would still have light, but light alone would not mean warmth in the human sense. It would mean photons crossing empty rock. The truth is likely varied. The galaxy is vast enough for many outcomes. Some red dwarf systems may be sterile, some may be chemically rich but lifeless, some may support microbial worlds, Some may host biospheres hidden beneath ice or atmosphere. Some may surprise every model built from Earth-based assumptions. The mistake would be to demand that all red dwarf planets share one destiny. In this way, red dwarfs force humility. They are common but not simple. Long-lived but not automatically gentle. Promising but not reassuring. They stretch the idea of habitability across time, reminding us that life depends not only on energy but on timing, violence, protection, chemistry, and chance. If an intelligent species evolved around a red dwarf, its experience of the universe would differ from ours at the most basic level. Its home star might dominate the sky as a deep red disk, perhaps fixed in place if the planet were tidally locked. The concept of a day might be geological, atmospheric, or cultural rather than astronomical. Sunrise and sunset, those rhythms that shaped human myth and biology, might be absent. Direction could matter more than time. Toward the star, away from the star, into the twilight, across the night. Such a civilization might develop under permanent gradients. One hemisphere too bright or too warm, another too dark or too cold, a habitable region shaped like a band between extremes. Architecture might follow the climate line. Migration might trace the boundary between heat and ice. Agriculture, if it existed, could depend on stable angles of red light. The sky might offer no familiar blue. Plants, if photosynthetic, might use pigments tuned to different wavelengths. Color itself could become a different inheritance. Their astronomy would also be different. A dim star gives less glare, but a tidally locked world with a stable night side might offer an extraordinary window into the cosmos. On the dark hemisphere, if the atmosphere allowed visibility, the stars might shine constantly. No daily sunrise would erase them. The galaxy could hang over the nightlands as a permanent archive. A civilization living near the twilight might build observatories in the cold dark, studying the universe from a side of the planet where the home star never appears. Their sense of time might be more expansive. Around a star expected to live for trillions of years, the death of the sun may not shape mythology in the same way. The great fear might come from flares, atmospheric loss, orbital shifts, geological decline, or cosmic isolation rather than stellar aging. Their star would seem ancient and reliable, even if its youth had once been violent. Their future might feel almost endless, at least until deeper cosmic processes began to matter. To imagine such beings is not to claim they exist. It is to recognize how strongly a star shapes possibility. Our philosophy grew under a yellow sun, with mornings, seasons, shadows, harvests, and a visible celestial clock. Under a red dwarf, mind itself might inherit another architecture. Time might feel less like a river of days and more like a vast pressure, constant and slow, with history unfolding beneath a sun that appears unchanged across civilizations. The universe will not remain as it appears now. Stars form from gas, and gas is finite. Galaxies evolve. Star formation rates change. Massive stars die quickly. Sun-like stars eventually leave the main sequence. Over immense timescales, the bright, active universe gradually gives way to a dimmer one. The process is not a sudden extinction of light, but a long redistribution of what remains. Red dwarfs stand near the end of that luminous sequence. Because they burn so slowly, they extend the era of ordinary starlight far beyond the lives of larger stars. Their presence means the universe's stelliferous age, the age when stars shine through fusion, may be prolonged by small suns. The final chapters of that age will likely be written in faint red light. Eventually, even red dwarfs must change. They cannot burn forever. Given enough time, hydrogen will be consumed, fusion will decline, and their structure will evolve according to physics that no current universe has yet displayed in a completed example. Models suggest that the smallest stars avoid the dramatic red giant phase of sun-like stars and end as dense remnants after incredibly long lives. But because no red dwarf has yet reached that state, their final evolution remains a theoretical future rather than an observed past. Beyond them lies a colder universe. White dwarfs cool. Planets drift in darkness. Stellar remnants interact, collide, decay, or wander depending on the ultimate fate of matter and cosmic expansion. Black holes may dominate the very far future before slowly evaporating through Hawking radiation, if current theory is correct. On timescales vastly exceeding stellar lifetimes, even the language of stars becomes obsolete. This is why red dwarfs matter so much. They are not the final objects in cosmology, but they may be the final ordinary stars. They preserve something recognizable, a sphere of plasma, a fusion engine, a source of warmth, a center around which worlds may orbit. They extend the familiar universe into an unfamiliar future. Thinking about red dwarfs changes the scale of human concern. We live in a civilization that struggles to plan beyond decades, sometimes beyond election cycles, markets, wars, and personal ambition. Yet the universe contains objects whose natural timescales make a million years seem brief. A red dwarf does not hurry because physics gives it no reason to hurry. It spends slowly, shines modestly, and survives by refusing extravagance. There is a temptation to turn that into a moral lesson, but the star has no intention. It is not wise, humble, patient, or disciplined in any human sense. It is matter obeying gravity, thermodynamics, quantum mechanics, and nuclear physics. Still, the image affects us. We are meaning-making creatures. We look at a small red star and see a form of endurance that our own world lacks. Earth is fragile because its conditions are temporary and rare in combination. Human civilization is more fragile still. We rely on a narrow climate range, stable agriculture, social memory, technological continuity, and a biosphere we did not design. Red dwarfs invite thoughts of survival across deep time, but they also expose the gap between cosmic endurance and biological vulnerability. A star may last trillions of years while a species burns through its own future in centuries. This does not make human life insignificant. Scale can diminish, but it can also clarify. The fact that we are brief does not empty our experience of value. It makes attention more urgent. We are the kind of universe that became aware of stars before our own star died. We can study objects whose futures exceed the age of the cosmos. We can imagine epochs no creature may ever witness. Briefness in this sense becomes the condition that makes wonder possible. A red dwarf will not remember us. It will continue burning after our languages vanish, after our cities are dust, after the continents have shifted beyond recognition, after the sun itself has changed beyond habitability. But for a moment, on one small planet around one temporary star, matter became able to understand that such things exist. That moment may be short, but it is not empty. Picture an observer in the far future if observers remain. The galaxy is older, quieter, and dimmer. Many bright stars have disappeared. The nebulae that once glowed with birth have thinned. The great blue stars are memories preserved in records, fossils, or mathematics. Above the observer, the sky is dominated by faint red points, long-lived stars that began their lives in an ancient universe and continue shining after almost everything else has changed. Around one of those stars, perhaps a planet remains warm enough for thought. Its inhabitants, if they exist, might look outward and reconstruct the lost brilliance of the early cosmos. They might know that there were once stars far brighter than their sun, stars that lived quickly and died violently, stars that forged the elements inside their bodies. They might see themselves as late arrivals, born beneath one of the universe's surviving lamps. Their science would be archaeology on a cosmic scale. The evidence of earlier eras would be faint, stretched, cooled, and distant. Galaxies beyond their gravitationally bound region may have disappeared beyond the cosmic horizon. The universe would feel smaller because expansion had hidden so much of it. The sky might contain fewer clues about the beginning. To understand the Big Bang, They would need relics, theory, and local memory. The early universe would be harder to see from the late one. This possibility gives our own era a strange privilege. We live early enough to see galaxies beyond our own in abundance. We can detect the cosmic microwave background. We can watch star formation, supernovae, black holes, exoplanets, and stellar nurseries. The universe has not yet withdrawn most of its evidence from view. We are not at the beginning, but we are early enough to witness variety. Red dwarfs will inherit a narrower cosmos. Their longevity may preserve light, but time may erase context. The last starfields may be filled with endurance and poverty at once. Stars that survive, skies that reveal less, worlds that continue under a universe increasingly emptied by expansion and age. Massive stars die with drama. They collapse, explode, and briefly outshine galaxies. Their deaths are visible across enormous distances. They leave behind neutron stars, black holes, expanding remnants, and clouds enriched with heavy elements. They make death spectacular. Red dwarfs follow a quieter destiny. Their endings are so delayed that the universe has not yet staged one for us to witness. That absence is part of their mystery. We can see the ruins of great stars. We can observe white dwarfs cooling, neutron stars spinning, black holes feeding, nebulae glowing from stellar remains. Red dwarfs offer no ancient graveyard of their smallest members. Their future is written in equations, not ruins. The most common stars in the galaxy are also among the stars whose complete stories remain unavailable. This gives the red dwarf an unusual narrative power. It is a star defined less by what it has done than by what it will continue doing. Its importance lies in duration. It stretches the present into the far future. It tells us that the cosmic age of light will not end when stars like the sun are gone. It will persist in lesser fires, in small spheres of plasma that keep converting hydrogen into helium with almost unimaginable restraint. To call such a star small is accurate. To call it minor is misleading. The late universe may depend on smallness. The last ordinary warmth may come from objects too faint for ancient humans to see. The final habitable worlds, if any exist, may circle stars that never inspired naked-eye myths. Grandeur, in deep time, changes form. A red dwarf's death will not be a sudden thunderclap in the cosmic dark. It will be the exhaustion of an immense patience. By the time the first of the smallest red dwarfs reaches its end, the universe will be older than any age our myths were built to imagine. The star will have outlived bright constellations, solar systems, civilizations, perhaps entire galactic structures as we know them. It will have turned quiet fusion into an almost endless act. There is something almost unsettling about the fact that the stars most likely to last are the ones we needed technology to notice properly. The human eye found the dramatic sky. Instruments revealed the durable one. This shift mirrors much of science. Reality often hides its most important truths outside ordinary perception. The closest star can be invisible. The most common stars can be absent from mythology. The longest-lived lights can appear weak. The red dwarf asks us to revise our instincts. Brightness is not endurance. Size is not destiny. Visibility is not importance. The universe does not arrange itself around what human senses find impressive. It rewards certain physical conditions with time, and in the case of red dwarfs, small mass becomes cosmic longevity. A faint star becomes a survivor because it burns slowly enough to remain. For a video essay, this is the heart of the story. The star that will outlive everything is not a blazing giant at the center of legend. It is a small red sun, one of trillions, perhaps unseen, perhaps unnamed by anyone who ever looked casually at the sky. It may shine over barren planets, or over worlds with atmospheres, oceans, ice, chemistry, or life. It may still be burning when our sun is a white dwarf, when Earth is unrecognizable, when the Milky Way has changed shape, when the universe has grown old and quiet. That image has the scale of science and the weight of elegy. Somewhere nearby, and almost everywhere across the galaxy, small stars are burning slowly. They do not care about us. They do not announce the future. They simply continue. Their light is faint enough to escape ancient attention and durable enough to cross ages that make human history disappear into a spark. When the last bright stars are gone, when the cosmic fires have thinned, when the universe has lost much of its youth, red dwarfs may still hold the line between light and darkness. They may become the last familiar stars, the final embers of the age of suns. And if any eyes remain to look upward beneath their crimson glow, they may see in that faint light what we are only beginning to understand now. The universe's longest stories are often written in the smallest flames. The story of red dwarfs is ultimately a story about time beyond experience. We can measure trillions of years mathematically, but we cannot feel them. The mind reaches for analogy and finds only failure. A human life, a dynasty, a species, a planet. Even the present age of the universe becomes too small for comparison. Red dwarfs force us to think in a scale where almost everything familiar becomes temporary. Yet their existence also gives the universe a strange tenderness. The cosmos is often described through violence, explosions, collisions, accretion, collapse, radiation, impact, extinction. Red dwarfs show another side of cosmic physics, a long continuity of faint warmth. They suggest that the universe's future will not immediately be silence. There will be light for a very long time, though weaker, redder, and scattered across an aging dark. They may never give us the drama of supernovae. They may never dominate the sky. They may never become symbols in ancient poetry unless some other civilization, under some other red sun, builds myths around them. Their greatness belongs to endurance rather than spectacle. They are the slowest promise stars can make, to keep burning long after almost every brighter thing has passed. And perhaps that is why they matter so deeply. A red dwarf is a small answer to the terror of cosmic endings. It does not save the universe from age. It does not prevent darkness. It simply delays the final dark by continuing to shine. In its low red glow, the future remains open for longer than intuition can bear. The star that will outlive everything may already be near us, too dim to see, too quiet to worship, too small to command attention. It is burning now with almost perfect indifference, spending its hydrogen grain by grain across ages that have not yet begun. Long after the sun is changed, long after our sky is gone, long after the bright universe has become a memory written in cooling matter and distant radiation, the red dwarfs will remain. Small fires, ancient futures, the last patient stars.